Welcome back, friends. In this video we will prove the second Sylow's theorem. Second Sylow's theorem is one of the very important theorem. In fact, the corollary of the second Sylow's theorem very important, and it will give us to really think in terms of a group action. Many problems can be attacked through this. Okay, let me give a statement first. Theorem. The statement says that similarly let G be a finite group and the order of G equal to n, that is p power alpha into m and p power alpha n, the usual notations. Then every p group is a subgroup of some p Sylow subgroup of G. I will explain. Any two Sylow subgroups are conjugate. I will explain. Okay, so what does it mean? Let's K be a p group, that means some p power beta, then where beta is less than or equal to alpha, then there exists a Sylow subgroup, Sylow p, in fact subgroup. The p mentioned says that K is a, let's say that p or H, let's say H is better notation. Okay, Sylow subgroup H. Okay, also if you have a two Sylow subgroup, then it's related by this, the H dash related by G inverse. This is called conjugate. Okay, I wanted to prove this. In a one stroke I am going to prove this. How? Proof. Let me explain little bit what I am going to do. Let K be a p group, p subgroup in fact of G, and H be a p Sylow. Sylow p or p Sylow, everything is like same. Subgroup. I wanted to prove in this way. I am saying there exists G belongs to G such that K sitting inside G H G inverse. In this way I proved both the statement. If I prove this, okay, because for this K I accommodated in another Sylow subgroup which is conjugate to this. In fact, if you choose K to be, another p Sylow, then K equal to G H G inverse, because order same, right? So I proved both the statements. So all I have to prove this statement. So remember that this is fixed, and I have to find that G. For this I am going to do something. Okay, what I am going to do, let x equal to G by H, left cosets. I am going to act G here like this. Like what? G A H. Sorry. G A H. That's it. That is like this is I am acting. Any basic group theory people knows this notations. I am going to observe this thing. Observation 1. Remember that P will not divide this cardinality of x, because cardinality of x is g by h, that is p power alpha m, p power alpha, maximum p power alpha is taken out, so it will not happen. Second, action is transitive. What does it mean? Single orbit, that is means single orbit. That means let's take AH and BH. I have to give a connection by G. So AH and BH inside X, I want to give a connection. So BH GAH, that is GAH. I want to choose G equal to BA inverse. Then I am done. So this is called the transitivity. Any two things are related by G or otherwise a single orbit. The stabilizer H as a element of X is H itself. How? Let's take the step of H. Step of H is nothing but G belongs to G, such that G comma H equal to H. See, remember that here H is an element. I am just considering it an element. GH equal to H means what? This means exactly H. That means G belongs to H and exactly H. Only I am collecting the element. Now this is the second restriction. First we restricted to the subset, invariant subset. Now we are restricting G acting on X, that is G by H. Now I am restricting this action to H. Restrict to H. Sorry, not H. Restrict to K. Now K acting on H, X. Remember that K is a P group. I proved fixed point theorem in previous lectures that I am going to use here. Since P does not divide order of X by fixed point theorem, you better watch the fixed point theorem. There exists a H belongs to X such that the stabilizer of AH equal to K itself. This is I proved long back in the previous, I am thinking of the 4th lecture, 6th lecture or something. You better watch. It means what? AH, any K, AH equal to KAH, that is again AH, that is equal to A inverse KA belongs to H for every K belongs to H. Is it same as saying, in fact, if and only if K belongs to AH A inverse for every K belongs to capital K. In that is if and only if capital K is a subgroup of this thing, right? So that is what I want to prove. Exactly. Hence the proof. That is what I want to prove. And from here, when we choose, again I will explain, when we choose K be any other Sylow P subgroup, then the order of K is same as AH A inverse order, so that must be equal to AH A inverse. So any two Sylow subgroup are conjugates. That I proved. So the key trick is here, the choosing the correct group action. Wherever you go, choosing the correct group action. Okay. So the corollary of this is very important. Corollary. Similarly, let G be a finite group and P divides order of G. Then the P Sylow Sylow subgroup H is normal, no, I want to say unique if and only if normal. Sometimes the is not needed. Proof. Let's assume normal implies unique. This is very important in a problem perspective. Let's see. G inverse equal to H, normal meaning. So that is equal to if I have another K that related by, this is for every G, related by some A H A inverse, right? But that is equal to H, right? This is by second Sylow and this is by normality. That's all. So K equal to H. So unique. Now unique implies normal. Let's do that. In general we can do that. This is characteristic, but I don't want to do that. This is easy. So K is unique. H is unique. G inverse order, both are same. Both are same, right? Because this is invariant. This is a conjugation homomorphism. Both are same. So G inverse order coincide with the order. So because of uniqueness, the H. So I said the unique group of order, the same order. Okay, that's a corollary. So that we are done. So normal, this is very important because we are going to prove later on, going to work out many problems related to not simple, and I needed this. Okay, let's see in the next video the third side. Here I wanted to add a bit more. I forgot to say, see, this is okay, but why this is kind of a conjugate to that I wanted to show. See, I told you the fact this transitive action and these things are happened. The transitive action come into play here. Suppose in general fact, let G acts on set in general factor. Okay, G acts on set, and let B belongs to orbit of A. Let A belongs to X and B belongs to orbit of A. What is the relation between step of A and step of B? Because A is related by G, right? So there must be something. So the claim is simple. Let's see. Step of B is nothing but a set of all G belongs to G, such that GB equal to let's use another notation, set of all W, or let's say A B. The notation I want to use, set of all W belongs to, okay, W equal to B. Does not move, right? That means set of all W belongs to G, WB equal to G, like say GA. So WB equal to B implies if and only if WB equal to GA, that is a B. WGA, I am replacing wherever G is there. Then what happens? WG G inverse A equal to A. So that means G inverse W G belongs to step of A. That implies W belongs to G inverse step of A G inverse. That means step of B is conjugate to. So we can see the step of A G inverse. So you can see that it's very easily the reverse way. If you change the role of A and B, you see the step of B is just conjugate. It's G only. G step of A G inverse. It's a conjugate. So this is how this is related, and this is heavily used here, heavily used somewhere here. Okay. Thank you.